Then the next ConvNet based model we shall be discussing is the residual network. This paper, entitled Deep Residual Learning for Image Recognition, was developed by Kamin He et al. Of Microsoft Research. Deep neural networks are more difficult to train. We present the residual learning framework to ease the training of networks that are substantially deeper than those used previously. We explicitly reformulate the layers as learning residual functions with reference to the layer inputs instead of learning unreferenced functions. We provide comprehensive empirical evidence showing that these residual networks are easy to optimize and can gain accuracy from considerably increased depth. On the ImageNet dataset, we evaluate residual nets with a depth of up to 152 layers. That is 8 times deeper than the VGG nets, but still having lower complexity. An ensemble of these residual nets achieves 3.57% error on the ImageNet test set. And these results won the first place on the IL-SVRC 2015 classification test. Now, driven by the significance of depth, a question arises: is learning better networks as easy as stacking more layers? So the question here was to know whether it's about just stacking up layers to gain more accuracy. An obstacle to answering this question was the notorious problem of vanishing/exploding gradients, which hamper convergence from the beginning. So when the gradients become too small in the case of vanishing and or too large in the case of exploding gradients, our model doesn't train well, simply because these gradients are used to update the weight parameters, and when these gradients become too small or too large, it becomes very difficult for our model to converge. Now, when deep networks are able to start converging, a degradation problem has been exposed. With the network depth increasing, accuracy gets saturated, which might be unsurprising, and then degrades rapidly. Unexpectedly, such degradation is not caused by overfitting. So what the authors are trying to say here is, the more we stack up these layers, there is this problem of degradation. So our model starts to drop in accuracy. And at first sight, we may feel like this drop is due to overfitting, but the authors are saying, as was proven, that this is not true and that the model actually degrades. We could see here that when we have this 20-layer model and this 56-layer model, after stacking up to get these two different configurations and then training our model, we find that the training error for the 56-layer is above the 20-layer model, showing us clearly how this 56-layer model, which normally should perform better than this 20-layer model, instead perform worse than this model. This was done on the training and also on the test. And from the two curves, it's clear that the problem here is not that of overfitting, but instead of degradation as we keep on increasing the number of layers of our model. So the two problems we have here is vanishing or exploding gradients, which lead to models not converging, and also the problem of degradation. And so they came up with a concept of residual learning. So let's consider h of x as an underlying mapping to be fed by a few stacked layers, not necessarily the entire net, with x denoting the inputs to the first of these layers. So from here we could have this x, which is the input, and then we have layers which have been stacked after this x input. So this first layer, the second layer, we could have many more layers. But what's to be noted here is there is a connection from this input to the output, giving us f of x plus x. So the stacking up simply is f of x. So after stacking up in the output right here, we have f of x. But then when we connect x to f of x, it gives us f of x plus x, which is now h of x. Rather than expect stacked layers to approximate h of x, we explicitly let these layers approximate a residual function f of x. The original function thus becomes f of x plus x. The degradation problem suggests that the solvers might have difficulties in approximating identity mappings by multiple nonlinear layers. With the residual learning reformulation, if identity mappings are optimal, the solvers may simply drive the weights of the multiple nonlinear layers towards 0 to approach identity mappings. Now, if the optimal function is closer to an identity mapping than to a 0 mapping, it should be easier for the solver to find the perturbations with reference to an identity mapping than to learn the function as a new one. So what the authors are trying to say here is, we have those weights, and in case of vanishing gradients, where those weights take values of practically 0, it's easier for this model to just learn this identity function instead of these parameters which are difficult to learn. But in the case where the weights can be learned normally without any issues of vanishing or exploding gradients, our model now behaves like a usual model where these layers are just stacked from the input to this output, and these weights are learned. So overall, the negative effects of vanishing and exploding gradients are reduced. Also, we should note that the shortcut connections in equation 1 introduce neither extra parameters or computation complexity. Now, the dimensions of x and f must be equal in equation 1. This is equation 1, which is this y equals f of x and wi plus x, where f of x plus wi is what we get after passing x through these two layers, and then x is gotten from this. So this is equation 1, and then the dimensions of x and f must be equal. So if it is not the case, we can perform a linear projection ws by shortcut connection to match the dimensions, as we can see. So we've added this linear projection ws. We can also use a square matrix ws, but we will show by experiments that the identity matrix or identity mapping is sufficient for addressing the degradation problem and is economical, and thus ws is only used when matching dimensions. This figure to the left shows us the VGG19 model, the 34-layer model, which is formed by stacking up those different conv layers, and then the 34-layer residual model, which has the skip or shortcut connections. Notice that in some cases we have those full lines, and then some cases dotted lines. And these dotted lines are the skip connections which link the inputs with outputs where there's a change in dimensions. And when there is this change in dimensions, in order for us to match this inputs with the outputs, we have two options. The shortcut, that's option A and option B. The shortcut still performs the identity mapping with extra 0 patterns for increasing dimensions. And then the B, that's the second method, the projection shortcut in equation 2, is used to match dimensions. But this is actually done in practical by one-by-one convolutions. Now if we look at the implementation that's during training, our implementation for ImageNet follows the practice in 21 and 41. Basically, these are some citations. We could go to 21. 21 is this paper by Krzyzewski and al. That's ImageNet classification with deep conv neural networks. This should be the AlexNet paper. And then 41 is this Simonian al, which is the VGG paper. And then the image is resized with its shorter side randomly shaped in the range 256 to 480 for scale augmentation. So this is already a data augmentation they've added into your implementation process. A 224 by 224 crop is randomly sampled from an image or is horizontal flip with the per pixel image subtracted, or rather the per pixel mean subtracted. The standard color augmentation in 21 is used, that's in the ResNet paper. We adopt batch normalization right after each convolution and before activation. Following this paper, we initialize the weights as in 13 and train all nets from scratch. We use SGD with a mini batch size of 256. The learning rate starts from 0.1 and is divided by 10 when the error plateaus. And the models are trained for up to 60 times 10 to the 4 iterations. We use a weight decay of 0.001 and momentum of 0.9. We do not use dropout, following the practice in this paper. In testing, for comparison studies, we adopt the standard 10 crop testing. And for best results, we adopt the fully convolutional form as in this paper and this paper, and average the scores at multiple scales. Here we have different versions of the ResNet. There's an 18 layer version, 34 layer version, 50 layer version, 101 layer version, and 152 layer version. And the 34 layer ResNet is better than the 18 layer ResNet by 2.8%. More importantly, the 34 layer ResNet exhibits considerably lower training error and is generalizable to the validation data. And then the 50, 101, and 152 layer ResNets are more accurate than the 34 layer ones by considerable margins, as we can find on table 3 and 4. We do not observe the degradation problem and thus enjoy significant accuracy gains from considerably increased depths. So we'll come back to this graph or this plot. We'll see how the degradation problem has been resolved by using these residual blocks, as we have here with the plain network. The 34 layer performs poorer than the 18 layer, but right here with the ResNet blocks, the 34 layer performs even better than this 18 layer. So we've succeeded in increasing the number of layers while maintaining a gain in accuracy. And then for the ImageNet classification task, the top 5% error for ResNets go right up to 5.71, and the top 1%, 21.43. Also notice that as we increase the number of layers, we move from this ResNet blocks made of just 2 layers, that is just 3 by 3, 3 by 3, to this ResNet blocks made of 3 layers. So we have 1 by 1, 3 by 3, and then 1 by 1 convolutions, which are now forming this ResNet blocks with obviously the skip or shortcut connections. This times 3 is to say that we repeat this thrice. Then the flops here stand for the number of operations done whenever inputs have been passed through each of these models. Let's see practically how we could build a simple ResNet 34 model from this ResNet block. So as usual, we have this custom conv2D, which is made of a conv layer and then the batch norm layer. Then to create this ResNet block, we have 2 3 by 3 conv-D layers right here. So basically, since we have channels which is gotten from an input which we pass here. So when we do ResNet block 64, for example, we're saying we have 64 channels. So we create this custom or this conv layer with 64 channels, and the filters are actually 3 by 3. Then we have the stride padding. By default, the stride equals 1, and we have padding same. Now in some other cases where we have a skip connection, we can add this self dotted. So if the skip connection is, if you have a skip dotted, so right here we could modify this to skip dotted. If your skip connection is dotted, then we have to include this 1 by 1 conv layer. We had seen this in the paper that when we have this skip connections, since the outputs don't match with the inputs, we need to include this 1 by 1 conv net layer, and that's exactly what we do right here. Now, so when the stride is equals 2, for example, like when we pass a stride of 2 in this ResNet block, this skip dotted variable takes the value true, and when it's true, instead of just connecting the input directly with these outputs and adding them up to have x1, we pass these inputs through a conf layer, and this conf layer is made of this 1x1 filters as we had said previously. And then that's exactly how we add up this X input, or rather this X modified input, with this output, such that they both have the same dimensions. And then we wrap this up with a ReLU layer before outputting it. So right here we could define the ReLU layer. ReLU is equals ReLU. So that's our ReLU, which has been defined, and then we could import it from this. So from this layers we import the ReLU layer. Then to create this whole ResNet 34 model, we'll simply stack up all the different layers as defined in the paper. So we have the custom comp2d max pooling, ResNet blocks which have been stacked, and then right up to this dense layer. Do the call. We have the X input which then yields this output as we get here, and then we can call our model and then use it as we wish.